Hello and welcome to week 12, module 12 of multivariate statistics. Believe it or not, folks, we've made it all the way. You've all done a great job. So in this week, we extend our discussion on structural equation modeling by going into a more advanced topic, but a very cool topic, which is mediation analysis. So we've talked about moderation before, way back in advanced regression. I think that was maybe module 3 or 4. But this week, we're actually going to talk about mediation models. So this is sort of the other side of the coin. We talk a lot about moderation versus mediation. And mediation, in many ways, is most easily estimated in a latent variable framework or what's called a structural equation modeling framework. So we're going to look at two examples of a mediation model. One is going to be a mediation model with observed variables. So nothing is latent. And that's basically going to be a path analysis. And another example is going to be a fully latent mediation model, where all of the sort of components of the mediation model are actually latent variables that have indicators. So just to show you a couple options, again, SEM is really flexible, and there are a lot of different things you can do. So I'm just sort of showing you a couple things that might be interesting for your work. So this is the module 12 R markdown file that's available on Canvas. And I'm going to first start by loading in some packages here. Again, the nice part about SEM is that it's usually pretty light in terms of packages. So we need tidyverse in case we need to manipulate some data, do some data management, cleaning, coding. The psych package is a go-to for kind of psychometric stuff. I don't know if we actually even need the psych package for this, to be honest. And then lavaan is our go-to for latent variable modeling. So we're going to load in some data on, I call this health data. So this is kind of like survey data related to health. And we're going to use the Haven package. And this file is called health old. The old part is just sort of a reference to the version of Stata that it came from. It's not, I think it's actually pretty current. It comes from Alan Aycock's recent book on using structural equation modeling in Stata. So I believe this is some survey data from Alan. So this is a pretty simple data set, but we're just going to try and work with these three variables in an observed variable framework to study mediation. So we have three variables here. We have conch, and that is conscientiousness. So that's a kind of a personality trait, right? Sort of being attentive to details or sort of like feeling normative pressure, right? If you feel like you should do something, that's evidence of conscientiousness. Behave is health-related behaviors. So this would be things like, I think primarily like washing hands, general kind of health, hygiene type behaviors. And then health is a measure of self-reported health. And all of these are sort of standardized scores. Again, these are observed variables. So they're all sort of mean 0, I think, and standard deviation roughly equivalent to 1, although there may be some variation here. So let's suppose that we are health policy folks or researchers, and we have this idea about a mediation model. In the mediation model, basically, we believe that behaviors are essentially a mediator between conscientiousness, a personality trait, and self-reported health. So health related behaviors are essentially our what do you call it? Our independent variable. Sorry, I'm not very well articulated this morning. So conscientiousness is over here on the left side of our diagram, and that is our kind of independent variable. Health-related behaviors are on the left side. Conscientiousness is on the right side, right? And then on the or in the middle, and then on the right side, we have health-related behaviors. So this could be a potential mediation model whereby people who practice health-related behaviors also tend to be more conscientious, and people who tend to be more conscientious also then have better measures of their health. So this is the model that we're going to try and specify here. And basically, to do this in lavaan, the format is actually pretty similar to stuff we've studied before, because a mediation model is basically just a form of regression. All we have to do is we have to define our A path, our B path, and our C path. And we do that just sort of by thinking how it looks visually in a path diagram. So here's our direct effect. And yep, sure enough, no wonder I was so thrown off. It is backwards. Okay, so conscientiousness impacts health-related behaviors impact health. Okay, thank you. That was throwing me off because I was like, that doesn't make sense. Okay, so someone being more conscientious impacts the amount of health-related behaviors that they are attending to, like washing hands, things like that. And their health-related behaviors in turn impact their health. But there might be a path, also a direct path, just between being more conscientious and health, right? Not just necessarily through health-related behaviors. Sorry, no wonder I felt like I was talking backwards there. So our direct effect here is just the relationship between health and conscientiousness. And this is the C path in our relationship. And notice I make a note here in your R Markdown file. This star convention, this asterisk, is just a way of defining specific paths in lavaan. So it doesn't necessarily mean multiplied by. It's just attaching this label, C, to this relationship, which is the relationship between conscientiousness and health. Okay, so all it does is it identifies a parameter. So that's our C path. Our mediator, we have two paths to look at for the mediator. We have the A path, which is the path between conscientiousness and behavior, and then the B path, which is the path between behavior and health. And I've defined those here too. So behavior is the outcome, and in the A path, and conscientiousness is the predictor. And notice all of these just use the tilde sign. The tilde is the sort of universal sign for a regression, right? Outcome regressed on predictor. And then the B path, in the B path, health, all the way on the other side of the diagram, is the outcome. And our mediator behavior is the predictor, and that's the B path. Okay, so that's the basic mediation model. We basically built a little triangle with those three variables all in the same place. Now we can go a step farther, and in fact, we need to, because we need to find out whether or not that indirect effect is actually statistically significant. And we talked about various ways of doing this. There's the what's called the Sobel test, the Baron-Kenny test, and then the bootstrapping test, which are three of the most common ways of interpreting this. But in order to do really any of these, I guess you could do Baron-Kenny without this. We need to actually define this indirect effect. And so this operator here, I think it looks like a person in a nose or something. It's kind of weird. It's a colon and then an equal sign. So the colon equal sign, that is used to define what's called a nonlinear parameter. So that is something that is not related to a specific parameter, but it's actually a product or a sum of parameters that have already been defined. And so the indirect effect, as we've studied in the lecture portion of this week, is actually the product between A and B, the A path and the B path. And so we define that here. AB is defined as the product of A times B. And then we can define the total effect, and we just call this total, is equal to or defined as the C path plus the product of the A and B path. So that's the direct effect plus the indirect effect. Okay, so these last two sections define these nonlinear parameters that we then can interpret to see if things are significant. Okay, so then we can go ahead and fit this model. So I just called it model. So that is going to be fed into lavaan as such. And then we fit it in the command. You can just say fit model. The command is SEM as opposed to CFA because we're now fitting more of a full SEM model. Our data are health old. Our estimator is MLR. And then two important things here. So I admit I dropped the ball on last week's lecture because I talked about this really cool fancy missing data feature in lavaan called FIML, full information maximum likelihood. But then what I didn't realize was that in order to get this to actually work in lavaan, you actually have to add a couple other options. So what we were doing last week was not truly FIML. It was using the robust maximum likelihood estimator, which is always a good thing. But we need to add a couple options to get this to actually run. So we need to add missing equals ML. That's the FIML option. And then kind of an under the hood option, which is fix.x equals false. I'm not going to go into too much detail about these. So this is missing equals ML is what activates the FIML capability. Fix.x equals false is basically changing how exogenous variables are defined in the model. For our purposes, because we're only using observed variables and not latent variables, this is something that we need to add. Otherwise, the software will not, again, apply this fancy missing data approach that we really like. And then we get a summary. So, okay, let's run all this. That's enough run up on that. And notice we get this sign right here. So this is a sign that you've done full information maximum likelihood. You get a message that says number of observations 500, and that's accurate. We actually had some missing data in this data set, but it has been accounted for using full information maximum likelihood. And then number of missing patterns. That is key because that's one of the key components to implementing this FIML algorithm. And so if you see that, it means that you've actually successfully run the fancy missing data approach. Then we get our test statistics, and look at that test statistic 0.000 for our chi-squared and 0 degrees of freedom. Now, why do we have 0 degrees of freedom? Because we're only using observed variables here. Most models that you run with only observed variables do not have any degrees of freedom. They're what we call just identified models. So in order to get fit statistics, you need to have degrees of freedom. And in this case, we don't, because everything is essentially predicting everything else, right? So all the variables are sort of either pointing to or away from each other. And so we don't have any degrees of freedom, and that's perfectly fine. That's what we expect. And then we get our estimates. So notice since we defined the A, B, and C path, those are now indicated here just to remind us. So the C path, that's my direct effect between health and conscientiousness, is positive and significant. So the more conscientious you are, the higher levels of health you report. Our A path is also positive and significant. So the more conscientious you are, predicts higher levels of health-related behavior. And our B path is significant. So the more health-related behaviors you practice, the more healthy you report being as well. So all three of our paths are significant. So according to Baron-Kenny, if the A and the B path are significant, then we do have a significant mediation. So that's sort of the first step. That's the Baron-Kenny test can be evaluated just basically by looking at this, which is cool. We can't yet define the Sobel. We'll get the estimates of the Sobel down below, but that at least gets us started. And then we get our intercepts and our variances, which aren't terribly helpful in this case. In a mediation model, you're most interested in your total effect and your indirect effect. So here is, notice under defined parameters, we now have an indirect effect. And it's the AB path, so it's the product of A and B. It's estimated to be 0.2, and it is statistically significant. So that is the Sobel test. This p-value is essentially the representation of the Sobel test. And so based on the Sobel test, we also have mediation. Mediation has occurred in this model. And then we get a total effect So that is the total effect of conscientiousness on health. And that is generated by adding together the estimate of the indirect path, which is AB, and the total effect. And so, and the direct effect, which is this path here, the C path. So essentially adding those two together, we end up with 0.475, and that also is statistically significant. So lots of good things in this model, right? So we do see mediation, and we can actually calculate a fraction of mediation, right? Just sort of by estimating. So 0.2 divided by 0.5 is about 40%. So 40% of the effect of conscientiousness actually flows through health-related behaviors, which is pretty cool. And you can start to estimate the extent to which those mediated relationships are actually taking place. If you want standardized results, that is also very easy. You can just put standardized equals true. I also put fit measures equals true here because I want to show you something. This is something that a trap that people fall into sometimes. So if you get fit measures, now notice the first thing you want to look for is your chi-square statistic, which is right here. And notice we have 0 degrees of freedom. So that means this model is just identified. So a just identified model, by definition, fits perfectly. So sometimes this throws you off because when you look down here at the CFI and the TLI, you're like, oh my gosh, they're equal to 1. This model's amazing. Now, the other hint that something might be going on, you don't get an estimate of the RMSEA. It's just all zeros. And you don't get an estimate of the SRMR. They're just all zeros. So this does not mean that your model fits perfectly. It means that you don't have any degrees of freedom to measure model fit. So all of these fit statistics really don't come into play when you're fitting a just identified model. So you could probably just take that part out if you wanted to. But standardized is true is great because then we actually get an estimate of the standardized coefficients. So down here, the far right column, these are all standardized coefficients. And we can get an estimate of the standardized indirect effect, which is down here, and the standardized total effect. Now, because these variables were basically standardized to begin with, we do not see big differences between the standardized estimates and the unstandardized estimates. But if you're using variables on different scales, which you often are, then you will see a big difference between the two, and you do want to use the standardized estimates. You can also obtain R-squared values. These are useful as a measure of effect size. Remember, R-squared back in our regression days is basically the proportion of the variation in a outcome variable that you're actually able to explain as a result of your model. And that's very easy. You use this command called lavaan inspect, and then you just list the name of our model, which is just called fit. And then you just say R2, which means R squared. So this command pulls a bunch of other kind of random fit statistics and indices to look at, but this just sort of gets us the R squared model only. And so here we get an R squared for health and we get an R squared for behavior. So our model explains 34% of the observed variability in health and 28% of the variability in behavior. So you can talk about it from an effect size standpoint as well, which is pretty cool. Okay, so the last thing, we've talked about how to evaluate whether or not mediation has occurred based on the Baron-Kenny test, which is basically just looking at the p-values for each path. And we've talked about how to evaluate the Sobel test, which is the indirect path AB that you defined at the beginning, whether or not that is significant. So the sort of current state of the art in the field is that a bootstrapped estimate of the indirect effect or the indirect paths is probably the best way to go. It's least vulnerable to bias due to small sample and other things. So a bootstrapped solution is actually something you can do in lavaan, which is really cool. So if you want to get bootstrapped standard errors and confidence intervals, which is kind of what is recommended. So this is going to be fit 2. We have to refit the model to do this because bootstrapping, remember, is a resampling procedure. We talked about this a little bit back in we talked about regression. And so bootstrapping, all that's doing is it's resampling from your original sample with replacement to kind of simulate the dimensions of the population. And so the command here is all the same. Fixed x equals false, missing equals ML. But to get bootstrapping, you put these two options on the end. SE equals bootstrap and bootstrap equals 10. Now, keep in mind, I have only included 10 draws because this can take a long time. Because remember, it's basically replicating your entire model that number of times and averaging the results. So I would recommend, so if you're going to like publish a paper, you should probably bump that up to more like 100. But this number is the number of draws, the number of times that the procedure is replicated. So for now, we're just going to do 10. And then when we get our summary, we can keep it exactly the same, except for on the end, we just put CI equals 0.95. And that gives us 95% confidence intervals that we can use to evaluate the significance. And so I wondered about this. So we can no longer use our MLR estimator when we're bootstrapping. So we can just drop ML. And I think we probably have to drop all our fancy missing data stuff too, if I'm remembering. So let me drop those out and just do SE equals bootstrap and bootstrap equals 10. There it goes. And then we get our summary. That was actually really fast for 10 draws. So we get a message here about extreme order statistics used as an endpoint. I'm not too worried about that in this case. It might just be like where the bootstrap replication started, but otherwise it looks like the model converged just fine. You get this message, lavaan ended normally after 15 iterations, which is good. And then we get this little message here, number of requested bootstrap draws 10, number of successful draws 10, which is pretty cool. And now notice we get confidence intervals. So for each estimate, so here's for example, the direct effect of conscientiousness on health. Here is the lower limit of the 95% confidence interval. Here is the upper limit. And so to evaluate the bootstrapped indirect effect, we come all the way down here and we're looking at that. So that is the lower and upper limit of the 95% confidence interval for the indirect effect, which is AB, and it does not contain 0. So that is indeed a good estimate, a statistically significant estimate. So long story short, that's basically what we're looking for here when we're trying to figure out whether or not this is a statistically significant relationship, indirect relationship in a mediation model. We can also, using the SEM plot command and the SEM plot package in the SEM paths function, we can also create a cool little visual here of our model, which we call fit. And that's kind of neat. I love to put a picture in a mediation model. I think it's just really clear. So here is the relationship, and these are standardized estimates because I've asked for standardized. So here's health behavior. Oh, sorry, it's flipped. It's throwing me off. So here is, okay, so health behavior, conscientiousness. Wait a minute, CPATH, conscientiousness, health, yeah. And conscientiousness behavior. Okay, so it's like turned this way. That's kind of confusing. So conscientiousness should be on the left side normally as we think about it, right? So conscientiousness flows to health. That's the C path. So 0.27 is the C path right here. Conscientiousness goes to behavior, and that is the A path. And this long one, which is kind of confusing, is actually the B path. So this is behavior impacting health. And you can also get that by kind of matching up the coefficients. I think there is like a layout, or yeah, I think it's like layout equals. So I think you can move the pictures around a little bit. I might be way off. Now I'm getting errors, so I don't necessarily know. But I think there is a way to rotate an SEM plot. Maybe it is rotate. What if we did rotate equals 2? Oh, wait, did that do anything? No, it's actually getting mad at me because I'm making things up. So I'll stop. But anyway, there is a way to get SEM plot to rotate that, so it looks like a traditional mediation model. But that's basically what it looks like. All right, so this is probably a good place to stop. Just to recap, this first part was all about how to run a mediation model with observed variables. So nothing latent. Basically, we looked at this relationship between conscientiousness, health-related behaviors, and self-reported health. And we fit it in a path analysis framework using lavaan. We talked about how to get standardized estimates. We talked about how to get R-squared values, and then finally how to bootstrap this thing to get sort of the best estimate of our indirect effect. So in part 2 of this video, we're going to use a different data set, a writing data set, and we're going to talk about how to make this happen with latent variables. So very similar approach, only this time we're doing it all with latent variables in a full structural equation model. So it should be fun. Hope that makes sense, and we will talk again soon.